Hello dear students, welcome you all. So in this lecture I am going to discuss about the logarithmic amplifier by using operational amplifier. With amplifier using operational amplifier. So in this article I am going to discuss about designing a circuit whose output will be equal to the natural logarithm of input, B input, right? So that circuit will then be called as a logarithmic amplifier, right? And we will design this circuit by making the use of a operational amplifier, right? We will design the circuit, we will understand its working, and then after we will drive the expression for the output voltage that I written here, that will be equal to the logarithm of input voltage, right? So for it, let's start with operational amplifier. We have taken a op-amp here. This is the output terminal. This is one input. This is other. It is going to be at virtual ground. This is the feedback path here, right? And here this one, this one, right? Now I'm going to make the supply voltage to the op-amp, right? And this is for load resistor taking output, right? Here I'm going to connect a PN junction diode. Right. This is PN junction diode. Now I'm going to put the values, put the resistances in the circuit. This is R1, right? This is RL, load resistor. This is V output plus B.Sc minus VEE, supply voltage gain. This is negative, this is positive, inverting terminal, non-inverting terminal. It is at virtual ground, right? And this is the input signal applied here, and it is again at virtual ground, right? So this is the circuit diagram of this logarithmic amplifier, right? Suppose current I is going from here and then it is going from here, right? I am writing it IE also because the same amount of the current will go toward this side. We know the current toward this side is nearly equal to 0. We have explained it many times, right? In case of operational amplifiers, I forget to place a virtual ground here, right? Now this is the required circuit, right? Now in order to understand the working of this circuit, so when we apply the input signal, the current will start flowing in this way, right? For the positive cycle, right? When it is positive, it is negative, current will go in this way. When the cycle is reversed, the current will then come in this way. So I will write down the equations, Kirchhoff's equations across this junction. So I will apply at this junction Kirchhoff's junction rule. Let this, I am calling it as junction A, right? This is junction B. So at junction A, we can see this current I is equal to this current I. I can say this I1, or it is I2 for understanding. I1 is equal to I2 because nearly zero current go toward this side. So what is I1? Now if I write it in terms of voltages, then it is V in minus, what is the voltage here? What is the potential here? Here it is 0, so here it should be 0. We have explained it in the earlier lectures. So V in minus 0 divided by R1, that is equal to I2. Or in place of I2, I am writing IF, right? To make it the forward current of a PN junction diode. Let's use IF subscript, that will forward current of a PN junction diode. IF, right? Here it also become IF, right? So I can say now IF is equal to V in upon R1. This is one equation. This is equation number 1, right? Now again apply the Kirchhoff's rule here at this junction. Now I am applying the Kirchhoff's loop rule. Clear? Kirchhoff's loop rule, right? I am coming from here, right? Here, right? And arriving at this point. It is at zero potential. It means V output, if I consider that the voltage drop across this PN junction diode is equal to BF, right? This is the voltage that drops across this PN junction diode. Then B output should be equal to minus VF, because B output plus BF should be equal to 0. Because if we are going from here to here, then this is the voltage, this is the voltage, their total sum should be equal to 0 here, right? Because it is at zero potential. So it means V output is equal to minus VF. Now we have B output is equal to minus VF, right? Now this is another equation, equation number 2. Now this is what IF was the current flowing through the PN junction diode. We know equation of PN junction diode that IF is equal to forward current of PN junction diode is equal to IS into e raised to power minus V upon eta and Vt, right? It is B output, right? Because output voltage is here. So this is the equation of the forward current PN junction diode equation. Here IF is the forward current flowing through the PN junction diode. IS stands for the saturation current. This Vt is the thermal equivalent of the voltage, right? And eta is a constant. Now we know B output is equal to minus Vf, right? Sorry, here it was positive. Earlier it was positive here, and it was Bf here. I mistaken here. Bf. Please correct it. It is Vf, right? Forward voltage of a PN junction diode. The voltage that is going to be dropped at this PN junction diode. Now, if I put Bf is equal to minus B output, then it will become minus. Whatever I mistaken, IF is equal to IS e raised to power minus V output upon eta Vt. Now, eta is, as I told you, it is a constant, right? and Bt is the thermal equivalent of the voltage, right? And Is is the saturation current. This is equation number 3. So if I compare equation number 3 with equation number 1, then I get V in upon R1 should be equal to Is into e raised to power minus B output upon eta Vt, right? So this will become further, when I will simplify it, I will take the logarithm, natural logarithm on the both the sides, then log of E, right, V in upon R1, right, upon, I also took this toward this side, then it become R1 Is. Let's take another step in which V in upon R1 Is is equal to e raised to power minus V output upon eta Vt. Now it is more symmetrical. Now we can take log here, then it becomes is equal to minus V output upon eta Vt. So if I further simplify it, then it becomes B output is equal to minus eta Vt natural log of V input upon R1 Is, right? So this is the expression for the output of this circuit, right? Equation number 4. Now you can see from this expression that, as I told you, that eta is constant for the given PN junction diode. If it is of silicon, it will have different value. If it is of germanium, or if it is of some other material, eta is fixed for that. Bt is thermal equivalent of thermal voltage equivalent of PN junction diode. Is is the saturation current for the PN junction diode. Again, it is a constant. R1 is fixed. So it means V output is directly proportional to the logarithm of B input, if all other things are quantities are fixed. So whatever I said in the beginning, and one important thing is it is negative also. It is negative because we are using the inverting terminal of the operational amplifier, right? So whatever I told in the beginning, that B output will be directly proportional to the logarithm of B input. So it is proved here in these equations. So this is the all about logarithmic amplifier, right? So it is going to perform the mathematical operation of log. If we want this operation in any circuit, right, particularly when we are designing computers for the computational techniques, then we can use this circuit for taking the log of the input signal, right? So this is all about it. So thank you very much.